This video is about rotational kinetic energy. So here's the idea. Say we have a thrown ball. So the thrown ball can have two types of motion and therefore two types of kinetic energy. So say this is the ball we just threw it this way, and when we threw it, we also gave it a spinning motion like this. So this V that we typically show with an object represents the V of the center of mass. But then while it's going through the air, so here's the motion of the ball, so while it translates through the air, pick a new spot here, it continues to have some velocity of the center of mass, but then it also continues to have this rotation. So when the ball is thrown, it may be thrown with a clockwise rotation, a counterclockwise rotation, or no rotation at all. So it's a separate motion and a separate type of kinetic energy. So the motion of the center of mass is called translational motion, and that's the kinetic energy that we've discussed up to this point. So the kinetic energy of translational motion is the equation that we already know, 1/2 mv squared, and now we're recognizing that this is the V of the center of mass, the motion of the center of mass. So we already know this equation. But now we're going to consider the motion of the rotation. So the rotational motion is the motion about the center of mass or around the center of mass. Actually, to be a little more generic, it's the motion around a rotation axis. Often that is the center of mass, but we could force it to be somewhere else. So let's say this in general. The rotational motion is the motion about a rotation axis. And so we say that has rotational kinetic energy. And that equation is 1/2 I, and I about the rotation axis, omega squared. So it's similar to the linear version, the translational kinetic energy, but instead of mass, we have moment of inertia, and instead of linear speed, we have angular speed. So now with these two types of kinetic energy, we need to expand the conservation of energy equation. So now we'll have the change in kinetic energy translational, which is the one we've been dealing with up to now, and now we add change in the rotational kinetic energy, and then the rest of the conservation of energy equation. All right, so all of this is the new conservation of energy equation. So let's talk about a rolling object, or more specifically, a freely rolling object. You know, if a car is accelerating, then it's not freely rolling. The gas is turning the wheels and propelling the car forward. Or if you hit the brakes, then the wheels are trying to slow down. But if the car is just rolling freely, or it's a bicycle or a ball that's just rolling along the ground, then all of those are freely rolling objects. In general, if we have like the thrown ball that we just talked about, then these two motions and therefore kinetic energies are completely separate. The velocity of the center of mass and then omega. So these are independent of each other. And so therefore, so are the kinetic energies. We might have some translational kinetic energy and no rotational, or vice versa, or whatever. But that's not the case with the rolling body or rolling object. These two velocities are tied together. Velocities. Okay, so this is how. So here's the ground. Here's the object that's rolling with some velocity. So the center of mass is moving along with some velocity. And that can only happen if it's rolling. Okay, so this is rolling along. Friction's making it turn. If there's a velocity of the center of mass, there must be an omega. It must be rolling. And if the velocity of the center of mass increases, if the ball goes faster and faster, or the wheel goes faster and faster, then omega must get bigger and bigger. So you can see sort of in general, they must be tied together. And then a little more specifically, if we change frames here, so instead of looking at it from the Earth's point of view, the Earth frame, instead we look at it from the center of mass frame. So in other words, we're moving along with the ball. So consider yourself looking at a wheel as it moves, but you're moving with it. you're say in a car next to it watching this wheel roll, then what you see is this part of the wheel moving, which would be the tangential velocity, and this part of the wheel moving, which would be the same tangential velocity, and the same for any part of the wheel. So any part of the wheel is going to have the same tangential velocity. But that tangential velocity is the same as the velocity at the center of mass back in the Earth frame. So this tangential velocity is the same as the velocity at the center of mass. So if you have a car moving at 5 miles per hour, then the tangential velocity of the wheel, assuming that it's not slipping, is also 5 miles per hour. So what we're saying is, for a freely rolling object, the velocity, the tangential velocity, is the same as the velocity at the center of mass. Okay, that was sort of the point of the whole discussion, and we're going to take advantage of that in a minute. There's another useful fact about a freely rolling object, and that's that the friction, so we're talking about the friction between the rolling object and the ground or the road, is static, so it's not slipping. And if the object is rolling freely, then the work by this friction is zero. And so I think if you think about conceptually what work means, adding energy or taking energy away from the object, in this case the rolling object, then if it's rolling freely, then I think it makes sense that that friction is not adding energy or removing energy, as long as it's rolling freely. Go back to the case of the car. If you hit the brakes, that means that it's not rolling freely, and the friction is doing some work. It's slowing the car down. Or if you hit the gas and the car is going faster and faster because of that, then the friction is adding energy to the car, so it's doing positive work. But if it's rolling freely, then that friction is not doing any work. The work is zero. Okay, so here's the bottom line then, the facts that we'll take advantage of. 2 facts about freely rolling objects. One is that the tangential velocity is the same as the velocity of the center of mass. And 2, the work by the friction force, which is static, is zero. Okay, so now we're going to take advantage of that. We're going to work a problem. It's going to be a conservation of energy problem, and you'll see how we'll take advantage of these 2 facts to solve the problem.